for a second to the erythrocyte production. When we talk about erythrocytes, remember, we are referring to the red blood cells. In our bodies, about every second, over 2 million red blood cells are destroyed. So they have to continuously be replaced. So the production of the actual red blood cell, that one is termed erythropoiesis, because it's strictly referring to the red blood cells. We produce about 1 million per second. The average lifespan is roughly 120 days. The development of that cell takes about 3 to 5 days. Over that time span, they're going to reduce in size. We've got, do you guys remember what that pluripotent was? Pluri meaning plural, potent. So it's going to be giving rise to more than one of these cells that we're dealing with, okay? And then, do you remember me mentioning the colony forming units? Because we've got the red cells, we've got the white cells. So what we got the platelets, all right? So we're gonna look at it as a cell being for that colony of cells. So the pluripotent is gonna give us the colony forming. So for this case, we're going to see that it's an erythrocyte colony forming unit. Does that make sense? From the pluripotent one. Now, there'll be other ones swinging off of this pluripotent because it's giving rise to more than one. Okay? But it'll give rise to that colony forming, which will give us, do you guys remember from part 1 when you were talking about blast, class, all that sort of stuff, site, okay? Do you happen to remember what blast stood for?
Was it to build up?
Okay, and it would be like our immature cell. So, with the blast, because the cell, the erythrocyte, we've got to have it at a point where it's an actual cell, okay? Meaning it's going to have the nucleus, it's going to have the organelles, okay? So it's termed an erythroblast, meaning it's going to give rise to an erythrocyte. Does that make sense? Now, as it begins to go through its development, when it has its nucleus and it has all of its organelles, it's making its product. The product for the red blood cell, hemoglobin. And it wants to make as much as it can because it wants to carry oxygen. Then, once it has developed the hemoglobin, what we're going to see is it begins to spit out those organelles to the point that we have our erythrocyte. And if you remember, cyte stood for mature cell. What did the clast do? Broke stuff down. Okay? So, told you. When we begin to have this process take place, the erythrocyte formation, okay, this forming unit, this colony, it has receptors on it. Cha-ching, receptors for erythropoietin from the kidneys. erythropoietin. What is it? It's a protein, a hormone. Now, from the kidneys, what has that got to do with my red blood cell production? Huh? Okay, kidneys are going to filter the blood. Something that I mentioned, heart beats. We get the pump through the aorta. One of the very first organs we hit are the kidneys. And guess what they can help detect? Well, when we look at that red blood cell and we think about hemoglobin, what does hemoglobin carry?
Oxygen.
So now we're going to have oxygen levels be detected. If it hits the kidneys, we don't have enough. They can release erythropoietin, and erythropoietin goes into the bloodstream to the receptors on this colony forming unit, and if it stimulates this colony forming unit, we're going to stimulate production of the erythroblast, which will develop into the erythrocyte, which is going to increase my ability to pick up oxygen and carry it to the tissues. Kind of cool, isn't it? So, when we have this take place, okay, this could be released in relationship to just normal, everyday functioning. If we're losing 2.5 million per second and we can replace it at 1 million, we're getting the production. If there happens to be a situation where there's been a lot of blood loss with the person, this can get produced by the kidneys and, basically help stimulate the red blood cell production. If the loss has been too great, it might not be quick enough to replace the blood that's been lost. You might have to be given blood, okay? It's, but as long as the recovery's going to be okay, you can get the blood, and roughly within 5 to 7 days, your body's beginning to replace what was lost. But it takes a while, okay? Now,
So, I don't know if this relates to it, but if you don't have airflow through your lungs, is that dealing with the blood flow as well?
Now, if you don't have airflow through the lungs, like in a chronic condition such as maybe emphysema or something like that, or are you thinking something more acute, like maybe asthma?
Something more acute.
Like asthma,
Yeah.
an asthma attack? Well, what'll happen is there will be a disruption in the blood flow, and that means that the cells are not picking up not picking up oxygen, dropping it off, picking up CO2, bringing it back. Now, when you have a situation like that, there's only a brief span of time, so most likely erythropoietin production is not affected. If it's more of a chronic condition, like emphysema, that sort of thing, that's going to be a situation where you're actually getting the air, but because the alveoli in the lungs, even though you're getting air, the alveoli in the lungs have changed shape, and their ability to exchange the gases is now affected. What happens is that's going to be a condition where the tissues of the body are going to be affected, because the gas exchange, not a lot they can do about that. So they put the people on oxygen to keep oxygen levels high, but it still doesn't mean that the exchange is taking place because of the shape of the alveoli. Now, when we have these red blood cells, and one of the things that becomes important for the red blood cells to do, iron plays an important part, because if we look at the hemoglobin, if we look at the structure of the hemoglobin, if you remember, globin, those were the 4 protein chains giving it the quaternary structure, and in the middle of each one was the heme group. The heme group attaches an iron molecule. Iron is one of those trace elements that we don't have to have a huge amount of in our bodies, but we do need it to be adequate. Now, people who are usually deficient in iron, we usually term that to be anemia, okay? Just not getting the oxygen to the cells as easily. The metabolism of iron in our bodies. Iron is, like we would think of, a metal, all right? So, how do we normally get iron? What's our source of it? Our diet. So we need to make sure that we have a diet that is sufficient in this mineral, this trace element that's important to the body. Now, let's kind of look at what takes place with iron. We take iron in our food. Now, we take in iron as either iron 2+ or 3+. Okay, I'm not expecting you to pay to really understand that, but you guys know that that means the little electrons, right? Okay. Now, we take it in, get it into the stomach. The acid that's in our stomachs takes the 3+ and turns it into 2+. Once we've done that, this gastroferritin, look what that gets to do. It gets to bind to the 2+. So if we bind to the gastroferritin, that will take it to the small intestines. Why do we have to make it to the small intestines? For something to be absorbed. If you look at the structure of the small intestines, like if you had an animal that we were dissecting, and if we were to cut out the small intestines, stretch it out, cut down, and fold it open. When you fold it open, it looks like all these finger-like projections. They're called villi. Do you remember that? Okay. Those finger-like projections, they are plasma membrane, and that's giving a lot of surface area. And if we have a lot of surface area, that means that there can be a lot of absorption into those cells. And we have how many feet of the small intestines? Roughly 22 to 23 feet. Think about that for a second. The trip that the food you eat has got to make before it can get to the large intestines and be pooped out. Okay? Now, as it makes that trip, it's running past all of those villi. And by running past all of those villi, absorption, 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 and the blood supply is amazing. So we have a direct connection from that cellular structure to the blood supply. so materials can move into the blood supply and then be transported to the tissues. Does that make sense? Now, it's transported to the small intestines so that it can be released for absorption. Once we get into the blood plasma, look what it does. It's going to connect. You remember those globs? Okay, so we're going to have a glob that picks up that iron. When we pick up that iron, we're going to make the way to the liver. The liver, some of that iron is going to get stored. We then can bind to this apoferritin and be stored in the liver. The rest of it will go to the organs that it's used and make hemoglobin. Now, myoglobin, one I haven't really mentioned.